Welcome to the Deep Dive, your shortcut to understanding the most fascinating research and insights out there. Today we're diving into a scientific quest. One so challenging, so complex really, that parts of it were genuinely thought impossible, just, beyond our reach. But now, cutting-edge artificial intelligence isn't just making it possible. It's actually pushing the boundaries of what we understand about, well, reality itself. Our mission today is to get deep into particle physics, specifically CERN's really formidable hunt for how the Higgs boson interacts with lighter quarks. We'll explore why these interactions have been so hard to pin down, how advanced machine learning is, cracking this incredibly complex code, and what these breakthroughs really mean for the standard model that's our basic theory of particles and forces. And along the way, we'll also touch on some broader and I think equally fascinating perspectives on scientific exploration, how knowledge itself evolves. So if you've ever wondered, how the universe gets its fundamental properties, or maybe how human ingenuity and tech combine to answer the biggest questions.
Well, then this exploration is absolutely for you. Get ready for some really compelling insights. Okay, let's unpack this a bit. The Higgs boson. It's that cornerstone of the standard model, right? Found at CERN's Large Hadron Collider back in 2012. And its whole deal, its superpower, if you like, is giving other fundamental particles their mass, like quarks. It really underpins so much.
That's exactly right. And what's really interesting is we've already had quite a bit of success confirming how the Higgs interacts with the heaviest quarks. The third generation ones, we're talking about particles like the top and bottom quarks. And these interactions, they line up perfectly, really perfectly with what the standard model predicts, which, that's not just a small thing. It's a huge validation for physics. Basically confirms a key piece of how mass originates for these heavy guys. But, and this is a big but, here's where the challenge gets much, much harder and maybe even more profound for, our everyday experience. Studying how the Higgs couples to the lighter quarks like the charm quark and even the up and down quarks, the ones that make up the protons and neutrons in every atom around us, that's remained largely untested territory. So this leaves us with a really significant open question. Is the Higgs really responsible for giving mass to the quarks that make up, well, everything we see, all the familiar stuff? Because until we properly test these lighter quark interactions, the picture just isn't complete.
That's such a critical point. So to look for these super subtle interactions, physicists can't just, point a telescope somewhere. They have to search meticulously for specific, really rare events. They're either looking for how a Higgs decays into other particles or how it's produced alongside them in those incredibly high-energy collisions at the LHC. And the specific search we're zoning in on today is for a Higgs decaying into two charm quarks. But not just any decay, it has to happen in events where the Higgs itself pops up alongside a pair of top quarks. You can just imagine how incredibly rare and difficult that specific signature is to spot. Amidst, billions of other particle interactions happening, it's like finding a needle in a haystack if the haystack was also exploding constantly.
Exactly. That exploding haystack analogy is pretty good, actually. And the real problem, the reason this was considered almost impossible just a few years back, is down to the quarks themselves. See, when quarks are produced, they almost instantly create these narrow sprays of other particles, hadrons, like protons and neutrons. We call these sprays jets. And it is incredibly hard to tell apart the jets coming specifically from charm quarks, especially in Higgs decays, from the huge number of jets created by other quark types, lighter ones mostly. The traditional ways of identifying them, what we call tagging, they just weren't efficient enough for these charm jets. Basically, the tiny signal from a Higgs charm event, it just got completely drowned out by all the background noise from other less interesting collisions. The signal-to-noise ratio was just way too low.
Okay. And this is where the story gets really interesting, right? Because this huge challenge wasn't just an obstacle. It actually demanded, right, and I'm quoting Sebastian Vuctrell here, a research fellow at CERN, paradigm shift in analysis techniques. So the CMS team, using this massive chunk of data collected between 2016 and 2018, they tackled two huge challenges. And they did it by deploying some seriously advanced machine learning techniques. Okay, so first challenge, accurately spotting those really hard to identify charm jets and all that particle mess. For this, they use something called a graph neural network, especially designed for this. Think of it like a super sophisticated pattern recognition system. It can sift through all the complex data from, energies, angles, types of particles within the spray, and pick out the unique signature of a charm quark, a pattern that, frankly, humans just couldn't reliably spot. Then, the second challenge, separating the real Higgs charm events from that overwhelming background noise, all those other collisions. For this, they used a transformer network. And yes, that's the same family of AI models behind things like ChatGPT. But here, it's cleverly adapted to classify particle events, not write text. It basically learns the story of a Higgs decay and tells it apart from all the other stories happening in the detector. It filters out the noise to find the rare signal. It's pretty amazing how adaptable these AI tools are.
Oh, absolutely. And what's truly impressive is just the scale and sophistication of the training involved for these AI systems. It's enormous. To teach this charm tagging system to spot its targets so well, researchers fed it simulations of hundreds of millions of jets. Hundreds of millions. This huge training data set let the algorithms learn the subtle, unique features of charm jets with way more accuracy and efficiency than we ever could with the older, sort of hand-tuned methods. This isn't just a small tweak. It's a fantastic example of how computational power, coupled with this cutting-edge AI, is genuinely unlocking questions we couldn't answer before. We're literally seeing patterns in data that were invisible just a few years ago.
Yeah, the results, the actual impact of using these AI methods, you're saying, has been groundbreaking.
Yes, absolutely groundbreaking. The CMS team achieved the strongest limits yet on how strongly the Higgs boson interacts with the charm quark. This isn't just inching forward, it's a major leap in our ability to probe these interactions. We're seeing them with a detail that was honestly unimaginable previously.
Strongest limits yet. How much stronger are we talking?
Well, to give you a sense, they reported something like a 35% improvement in precision compared to the previous constraints on this specific interaction. That's a really big jump. And what that extra precision does is it places really significant bounds on any potential deviations from what the standard model predicts. It basically shrinks the wiggle room, the space where unexpected new physics or particles might be hiding in that Higgs charm interaction. So it either confirms the standard model more strongly, or if there are deviations, it gives us a much clearer target to aim for.
Right. Okay, so it tightens things up considerably. It limits the unknown, at least here. Jan van der Linden, a researcher at Ghent University, called these findings a major step. Makes sense. So with this big step taken, what's next? Where do they go from here?
Well, the immediate goal is to keep refining these AI techniques, make them even better, and crucially, collect more data. Lots more data from the upcoming LHC runs. You see, the more data you feed these AI models, the better they get trained, the more fine-tuned they become, and the more solid our conclusions will be. And the hope is that this combined effort, better techniques, more data could eventually let CMS, and also its partner experiment ATLS, directly confirm the Higgs decaying into charm quarks, like see it clearly. And that confirmation, that would be a huge milestone. It would give us a much more complete picture of the Higgs role in generating mass for all quarks, not just the heavy ones. It'd be a really vital, definitive test of the standard model, which is, 50 years old now.
It's genuinely inspiring seeing how far we've come, especially with these new tools like AI accelerating things. But, as we push these frontiers, it does make you think about scientific progress itself. How do we sort of navigate new discoveries, bring in new tools, and stay open to different ways of seeing the universe? Because, let's be honest, not everyone agrees on the basic frameworks we use. Sometimes the very foundations get challenged.
And that raises a really important question, I think, for everyone involved in science, and maybe even for you listening. What happens when our established scientific frameworks, even something as solid-seeming as the standard model, face intense scrutiny, or completely new interpretations? It's a necessary part, maybe sometimes uncomfortable, but a necessary part of the scientific process. It pushes us to constantly recheck and improve our understanding.
Yeah, and if you look around at the discussions happening, especially around fundamental physics like this, you definitely find perspectives that are quite critical of mainstream science, even critical of, the peer-reviewed journals we often rely on. These critiques, which I think are important to acknowledge, sometimes argue that these established publications might, maybe unintentionally, lead us to misinterpret things.
Right. For instance, you see arguments suggesting that maybe mainstream publications sometimes define differences as sameness as differences, that kind of thing. These critiques might point to examples where, in their view, maybe certain particles are treated as identical despite having different properties, or maybe phenomena like vortex structures in space are overlooked or require excessive proof. While core concepts like space and time are constantly debated, the argument is that maybe traditional journals, while vital, can sometimes become a bit ideologically outdated, maybe entrenched in vested interests, and that could potentially slow down really revolutionary ideas.
And out of that critical viewpoint, you get these alternative ideas about the universe. One example is something called topological vortex theory, or TVT. Now, this theory suggests something pretty radical, that the universe isn't just particles and formulas. Instead, imagine reality as this constantly shifting, interacting web of, whirlpools, basically, swirling structures in space-time itself. These are the topological vortices, and their complex fractal patterns are what we actually perceive as matter and energy. It's a totally different picture, less about particles, more about dynamic geometry.
And this perspective suggests a really profound shift in thinking, moving away from something like universal gravitation towards a bigger idea, maybe universal spin, as the key driver of interactions. It also argues that our current math, while powerful for what we do now, might not be enough to really describe these vortex phenomena, that we might need entirely new theoretical tools. It's just a powerful reminder, isn't it, that even while we're celebrating these huge breakthroughs within our current scientific framework, there are always other ways to look at the universe and at the scientific process itself. As philosophers of science like Thomas Kuhn pointed out, paradigm shifts can totally reshape how we see everything.
What an incredible journey we've taken today. From the Higgs boson through that really tough challenge with the lighter quarks and seeing how advanced AI is making that quest not just possible, but actually quite probable now. It's just amazing to see that blend of human ingenuity, cutting-edge tech, and rigorous science uncovering these deep secrets.
Yeah, and we've also touched on those bigger philosophical questions that just naturally come up with discoveries like this. How scientific ideas evolve, get refined, and sometimes get challenged from completely different angles. It really makes you think about how knowledge changes over time and why it's so important to keep re-examining our basic assumptions, even the ones that feel really solid.
So as we keep using these incredibly sophisticated tools, like AI, to probe the universe, here's something to think about. How much do our tools, the very instruments and methods we use, end up shaping the questions we ask, and therefore the answers we find? And maybe, just maybe, what possibilities are we missing if we aren't constantly questioning the very foundations of how we inquire, if we aren't open to radically different ways of seeing the world? Something for you to ponder as you reflect on all this.